Tonight, we're going to travel to a place that no telescope has ever reached, and no human mind has ever truly been able to hold. A place before colour, before sound, before the concept of a star even existed in the universe. Not the distant past, not billions of years ago in some abstract academic sense, but the actual literal darkness that filled all of space, every corner of everything that exists, before a single point of light had ever been born. Most people, when they think about the beginning of the universe, picture fire, a blinding explosion, a flash of creation. But here is the thing most people don't realize. Before the fire, there was something else entirely. Something vast, cold, invisible, and in many ways more mysterious than the stars that came after it. Imagine standing in absolute darkness. Not the darkness of a room with the lights off, not the darkness of a night sky between the stars, but a darkness so complete, so total, and so deep that it stretched in every direction for hundreds of millions of light years with nothing to break it. No glow on the horizon, no distant point of fire, just an invisible ocean of gas, slowly drifting, slowly cooling, carrying inside it the faintest whispers of structure. Ripples so small they were almost nothing. Patterns written into the fabric of space by events that happened in the first fractions of a second after the Big Bang. That darkness had a name. Scientists call it the Cosmic Dark Age, and it lasted for nearly 200 million years. By the end of tonight, you're going to understand exactly why that silence was not empty, why it was in fact the most important era the universe has ever passed through. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. And here is what makes this truly terrifying, in the most beautiful sense of that word. Everything you are, every atom in your body, every thought you have ever had, every star you have ever looked at on a clear night, was already present in that darkness, not yet formed, not yet lit. But there, in seed form, folded into the cold hydrogen gas drifting silently through a universe that had not yet learned how to shine. The first star had not been born. The first element beyond hydrogen and helium did not yet exist. And yet, in some profound and almost impossible to grasp way, everything that would ever exist was already waiting, quietly, patiently, in the dark. Now, let's begin. There is a moment I want you to picture. Not a dramatic one, not an explosion or a collision or a burst of colour across the sky, just stillness, just an infinite featureless dark stretching in every direction, farther than any number you have ever tried to hold in your mind. No stars, no galaxies, no light of any kind, just cold gas slowly drifting, slowly cooling, and a silence so absolute that the word silence barely covers it. That is where we're going tonight. That is the place this story begins. Most of us, when we think about the cosmos, start with stars. We look up at the night sky, and we see them scattered across the dark like embers from a dying fire, and we assume that this is what the universe looks like, that it has always looked something like this, bright points of light suspended in darkness. But that picture is only true for a tiny slice of cosmic history. For a vast, almost unimaginable stretch of time before those lights existed, the universe looked nothing like what you see when you step outside on a clear night. It looked like nothing at all, and I mean that almost literally. Here is the thing most people don't realize. The universe is approximately 13.8 billion years old. That number is so large that it stops meaning anything the moment you try to feel it. But buried inside that number is a period of time that almost never gets talked about. A stretch of roughly 200 million years, early in the universe's history, when not a single star existed anywhere. Not one. Not a faint one. Not a distant one. Not even a small unstable one flickering somewhere in the dark. The cosmos was completely, utterly lightless. Scientists call this period the Cosmic Dark Age, and once you truly understand what it means, it changes the way you think about everything that came after. To reach that darkness, we have to go back, way back, past our sun, which is about 4.6 billion years old, past the oldest stars in our galaxy, some of which are nearly as old as the universe itself, past the formation of the first galaxies, past almost everything we can see, even with our most powerful telescopes. We have to go back to a time when the universe was so young and so different from what it is today that it barely resembles the cosmos we know. A time when the temperature of all of space was still dropping from the unimaginable heat of creation, when matter itself had only just figured out how to become atoms, when the future was not written in any star because no stars had yet been born to write it. Imagine the universe as an ocean, not an ocean of water, but an ocean of gas, hydrogen mostly, about 75% hydrogen, about 25% helium, and almost nothing else, because almost nothing else existed yet. Every heavy element, every piece of carbon, every oxygen atom, every trace of iron or calcium or silicon had not yet been forged. The furnaces that would create those elements, the cores of stars, had not yet ignited. So what filled the universe was this vast, dark, featureless gas cloud, slowly spreading outward from the chaos of the Big Bang, slowly thinning, slowly cooling, carrying almost no structure and almost no variation, just gas, everywhere, in every direction, as far as the universe extended, and yet that gas was not perfectly uniform, it was not perfectly smooth. Folded into it, at scales too small to see and too subtle to detect without very careful measurement, were the faintest possible variations in density. Some regions of the gas were, by an almost invisible margin, slightly denser than others. Some pockets had, for reasons rooted in the quantum physics of the first fractions of a second after the Big Bang, just a tiny bit more matter packed into them. These variations were so small that if you had been floating inside that primordial gas cloud, you would never have noticed them. You could have drifted through that darkness for millions of years and perceived nothing but sameness. But those tiny variations were everything. They were the seeds of every star, every galaxy, and every living thing that would ever come to exist. This is one of the most terrifying and beautiful ideas in all of science. The entire future of the universe, including you, was already written into those faint ripples in the pre-stellar dark. Not consciously, not by design as far as we know, but structurally, mathematically, physically. The way a wave is written into the surface of water before it has yet risen into a visible shape. The cosmos was already carrying its own future inside it, in a language of density and gravity that would take hundreds of millions of years to fully speak. So when we talk about what existed before the first star, we are not talking about nothing. That is the critical thing to understand. We are talking about something invisible, something dark, something cold and slow and structureless by the standards of the bright universe we live in today. But something real, something physical, something that obeyed laws and responded to forces and carried within it the raw material of absolutely everything. The cosmic dark age was not an absence, it was a presence. It was the universe in its most elemental form, stripped of every feature we associate with the cosmos, and yet full, completely full, of potential. There is a quietness to that image that I find oddly comforting, especially at night. The idea that before the noise and the fire and the billion-year drama of cosmic evolution, there was this long, patient stillness, a dark ocean waiting to learn what it was, waiting for gravity to whisper to it, waiting for its own density to pull it slowly, imperceptibly together, until somewhere, in some unremarkable corner of the invisible dark, a cloud of hydrogen gas reached the point of no return. Began to collapse, began to heat, began to glow, and the cosmic dark age ended, not with a bang, but with the quiet ignition of the very first star the universe had ever known. But we are not there yet. That moment is still hundreds of millions of years away from where we are standing right now. Right now, there is only the dark, and in the dark there is more to discover than you might think, because the darkness itself, the gas and the cold and the invisible structure folded into it, is not a waiting room for the real story. It is the real story. It is the foundation. It is the ground on which every light in the universe was eventually built. And to truly understand the cosmos, to truly feel the scale and the strangeness and the almost impossible improbability of stars and planets and life, you have to sit with that darkness for a while. You have to let it settle around you. You have to feel, even just faintly, what it means that something was here before the first light, that the universe existed in the dark for a very long time, and that somehow, out of that dark everything came, Before the darkness, there was fire, and before the fire, there was something that we do not have a word for. Something so extreme, so far outside the boundaries of anything we can observe or recreate or even fully describe with mathematics, that physicists tend to simply call it the singularity and move on. A point of infinite density, infinite temperature, infinite strangeness. And then, approximately 13.8 billion years ago, it expanded. Not exploded outward into empty space, the way a bomb goes off in a room, but expanded, space itself stretching in every direction simultaneously, carrying energy and matter with it. The event we call the Big Bang was not an explosion in space, it was an explosion of space, and what it left behind in its first few minutes would determine everything that ever came after. I want you to think about what the universe was like in those first 3 minutes, because it is almost impossible to overstate how alien it was. In the first fractions of a second, the temperature of the entire universe was not millions of degrees, not billions of degrees, not even trillions of degrees. It was something in the range of 100,000 trillion degrees, a number so large it has no meaning in everyday life, no analogy that truly works, no object you can point to for comparison. The entire observable universe, all the space that would one day contain hundreds of billions of galaxies, was compressed into a region smaller than a single atom. Everything was energy. Everything was radiation. There was no matter in any form we would recognize. There were no atoms, no molecules, no particles of the kind that make up you and me and every star in the sky. There was only a seething, unimaginable plasma of pure energy. In the first second, as the universe expanded and cooled at a rate that staggers the imagination, the first subatomic particles began to condense out of that energy. Quarks first, combining almost immediately into protons and neutrons, then electrons. These are the fundamental building blocks of all ordinary matter. Every proton in your body, every neutron in the nucleus of every atom in every cell of your body was forged in that first blazing second of existence. Not in a star, not in a nebula. In the opening heartbeat of the universe itself, when the cosmos was smaller than a grapefruit and hotter than anything that has ever existed since. That is where the raw material of you first appeared. By the time 3 minutes had passed, something remarkable was happening. The universe had cooled enough, just barely enough, for protons and neutrons to begin fusing together. This process, which physicists call Big Bang nucleosynthesis, lasted only a short while, perhaps 17 minutes in total. A 17-minute window during which the entire elemental budget of the early universe was set. Hydrogen nuclei, which are simply single protons, formed in the greatest abundance. Helium nuclei, made of 2 protons and 2 neutrons, formed in substantial quantities. Trace amounts of lithium and a handful of other light elements appeared as well. And then, as the universe continued to expand and cool, the temperature dropped below the threshold needed for fusion to continue, the window closed, the cosmic kitchen shut down, and the elemental composition of the universe was fixed at roughly 75% hydrogen and 25% helium, with almost nothing else. That ratio would not meaningfully change for hundreds of millions of years. Here is the thing most people do not realize about those first 3 minutes. They were not just a chaotic random explosion. They were extraordinarily, almost suspiciously precise. The rate of expansion, the ratio of matter to antimatter, the strength of the forces governing nuclear fusion, the density of the early plasma, all of these had to fall within incredibly narrow ranges for nucleosynthesis to produce the hydrogen and helium the universe needed. A slightly faster expansion and protons would never have had time to fuse into helium at all, leaving a universe of pure hydrogen. A slightly slower expansion, and almost everything would have fused into helium and heavier elements, leaving almost no hydrogen to fuel the stars. The first 3 minutes walked a razor's edge between 2 kinds of cosmic sterility, and the universe survived it. Barely, in the cosmic sense of the word. But even after those 3 minutes, after the first particles had formed and the first nuclei had fused, the universe was still not transparent. It was still not the dark, gas-filled ocean I described in the last chapter. For the next 380,000 years, the cosmos remained a dense, opaque plasma. A fog of charged particles, protons and electrons moving freely, constantly colliding with photons of light so that no light could travel more than a tiny distance before being absorbed and re-emitted. The universe was a hot, glowing, impenetrable mist, brighter than anything we can imagine, completely opaque in every direction. You could not have seen through it. There was nothing to see. There was only the glow, the heat, and the relentless expansion of space carrying everything outward. And then, 380,000 years after the Big Bang, the universe crossed another threshold. The temperature had dropped to roughly 3,000 degrees, cool enough for electrons to finally slow down and be captured by protons, forming the first complete stable hydrogen atoms. Physicists call this moment recombination, though it is a slightly misleading name since the electrons and protons had never actually been combined before. In an almost incomprehensibly short period of time, the entire universe transitioned from an opaque plasma to a transparent gas. The fog lifted. For the first time in cosmic history, light could travel freely through space without being immediately absorbed. Photons that had been trapped in the plasma for 380,000 years suddenly streamed outward in every direction. The universe became, in a sense, visible. But here is the strange and haunting thing about that moment of clarity. When the fog lifted, there was nothing to see it. No eyes, no instruments, no conscious observers of any kind. The light flooded out into a universe that was now transparent, cold, and dark in a new way, because the matter, the hydrogen and helium gas that had just formed, did not glow. It did not emit light. It simply drifted, cooling, spreading, structureless, and silent. The photons that were released at recombination are still travelling today. We can detect them as a faint microwave glow that fills the entire sky in every direction. The oldest light in the universe, a direct fossil of that moment when the cosmos first became transparent. But in the universe itself, at that moment, there was no one to see the light go on. And after it did, the dark closed in, the gas cooled, the universe went quiet, and the long wait for the first star began. There is a name for what came after recombination. After the plasma fog lifted, after the first hydrogen atoms formed, after the photons streamed outward into a universe that had just become transparent for the first time. Scientists call it the Cosmic Dark Age, and the name is not poetic exaggeration. It is a precise literal description of what the universe was like for a stretch of time so long that it makes all of recorded human history feel like a single breath. Roughly 200 million years of complete unbroken darkness. No stars, no galaxies, no sources of light of any kind anywhere in the observable universe. Just gas, gravity, and silence on a scale that the human mind was not built to hold. I want you to really sit with that number for a moment. 200 million years. The dinosaurs went extinct approximately 66 million years ago. That means the Cosmic Dark Age lasted more than 3 times the entire span of time between us and the dinosaurs. 3 times. And during every single one of those years, the universe contained nothing that glowed, nothing that shone, nothing that radiated heat or light or any form of electromagnetic energy detectable by any instrument we could build. If you had been there, floating in that primordial gas in some impossible act of time travel, you would have experienced a darkness so complete and so absolute that the darkness of the deepest cave on Earth, the darkness of a windowless room at midnight, would seem blazingly bright by comparison. There would have been nothing, in every direction, for as far as the universe extended. The gas itself was cold, not cold in the way that deep space is cold today, though that is cold enough, roughly minus 270 degrees on the Celsius scale, just barely above absolute zero. In the early Cosmic Dark Age, the universe was somewhat warmer than that, still cooling from the heat of recombination. But it was cooling fast in cosmic terms, and it was dark in a way that went beyond the absence of visible light. The entire electromagnetic spectrum was empty. No radio waves from distant transmitters, no infrared glow from warm bodies, no ultraviolet radiation, no X-rays, no gamma rays from exotic processes. The universe had turned off every light it had ever had, and it would not turn one back on for hundreds of millions of years. Here is what makes the Cosmic Dark Age so difficult to truly imagine. It was not just dark the way night is dark, where you know the sun is on the other side of the planet and will return in a few hours. It was not dark the way deep space looks dark between the stars, where you know that if you travelled far enough, you would eventually reach another source of light. During the cosmic dark age, there was no other side. There was no source of light to travel toward. The darkness was not a gap between bright things. It was the entire universe, completely and uniformly dark in every direction without exception. If you somehow survived in that environment, you could travel for millions of light years in any direction, and your experience would not change at all. Dark gas, cold temperatures, silence, the same in every direction forever. And yet the universe was not standing still during those 200 million years. It was working. Quietly, invisibly, in ways that would only become apparent much later, the forces of physics were operating on that cold gas with extraordinary patience. Gravity, the weakest of the fundamental forces, and yet the one that operates across the largest scales, was doing what it always does. It was pulling. Everywhere, simultaneously, the slightly denser pockets of gas that had been seeded by quantum fluctuations in the earliest moments of the Big Bang were drawing surrounding material toward themselves. Not quickly, not dramatically. In the cosmic dark age, this process was painfully slow by human standards. But over millions of years, and then tens of millions of years, and then 100 million years, those density variations began to amplify. The slightly denser regions became denser still. The slightly emptier regions became emptier. The universe was sorting itself, in the dark, without any light to illuminate the process. There is something I find deeply strange about this. The most consequential structural transformation in cosmic history, the process by which a featureless gas cloud began to organize itself into the filaments and knots and sheets that would eventually become galaxies and clusters of galaxies, and the large-scale structure of the entire observable universe, happened in total darkness. There was no witness. There was no light by which any observer could have watched it. The universe was literally building its own future in the dark, guided only by the mathematics of gravity and the initial conditions set down in the first fractions of a second after the Big Bang. In the dark, it was becoming something, and it did not need light to do it. Scientists have studied the cosmic dark age primarily through inference and through the faint signals it left behind. We cannot see it directly. Our telescopes detect light, and during the dark age there was no light to detect. But we can see its edges. We can observe, with instruments sensitive to radio waves, the faint signature of hydrogen gas from that era. A specific wavelength of radio emission, called the 21 centimeter line, is produced when hydrogen atoms in their ground state undergo a tiny transition in their internal energy. That signal, stretched and redshifted by the expansion of the universe over billions of years, carries information about the distribution and temperature of the gas during the cosmic dark age. Several major radio telescope projects around the world are currently trying to detect and map this signal in detail. What they find when they succeed will be the closest thing we have ever had to a direct observation of the era before the first star. But for now, much of what we know about the dark age comes from modelling, from calculation, from working backward through the physics of what we can observe today, and extrapolating into the unlit past. And what those models tell us is consistent and clear, and in its own way rather beautiful. The universe during the cosmic dark age was not random. It was not chaotic. It was structured, quietly and invisibly, by physics operating with perfect consistency across unimaginable distances. The darkness was not disorder. It was the universe in a state of deep, patient preparation, organizing itself, waiting, building, in the cold and the silence, toward the moment when the first cloud of gas would reach the threshold of collapse, when gravity would finally win its long, slow battle against pressure and thermal energy, and when, for the first time in cosmic history, hydrogen would begin to fuse, when the first star would ignite, when the darkness would finally, after 200 million years of absolute night, begin to end. Picture the largest ocean you can imagine, not the Pacific, though the Pacific is so vast that if you stood at its centre, you could not see land in any direction, and the horizon would curve away from you in a perfect unbroken circle. I mean something larger, something incomparably, almost offensively larger. An ocean with no surface and no floor, no shore in any direction, extending outward in 3 dimensions rather than 2, filled not with water, but with gas so thin that by the standards of a laboratory vacuum it would barely register as matter at all. Now scale that ocean up until it contains the volume of the entire observable universe. Every cubic light-year of space, in every direction, for 46 billion light-years in every direction from where you are floating. Fill all of that with cold hydrogen and helium gas. That is the invisible ocean of the cosmic dark age. And you are somewhere inside it, in the dark, with no landmarks, no edges, and no light. The density of that gas was extraordinarily low. We need to be precise about this because the word gas might conjure the wrong image. You might picture fog, or steam, or even the thin air at the top of a mountain. But the primordial gas of the cosmic dark age was nothing like any of those things. In the densest regions of that early universe, you might find perhaps a few hundred hydrogen atoms per cubic meter. In the emptier regions, far fewer. Compare that to the air in the room where you are right now, which contains roughly 10,000 trillion atoms per cubic meter, and you begin to appreciate just how astonishingly thin and sparse this primordial ocean truly was. It was, by almost any everyday standard, indistinguishable from a perfect vacuum. And yet it was everywhere, and in its totality, it added up to all the ordinary matter the universe would ever have. This gas was not static. It was moving because the universe itself was expanding, carrying everything in it outward in every direction simultaneously. But it was also moving in smaller, more local ways. Atoms within the gas collided with each other, slowly and rarely given the extreme thinness of the medium. Tiny currents and eddies formed and dissolved on scales of thousands of light-years. The gas had a temperature, dropping steadily as the universe expanded and cooled, and that temperature meant the atoms were in motion, vibrating with thermal energy that provided a kind of pressure, a resistance against the pull of gravity. For a long time, during the first phase of the cosmic dark age, this thermal pressure was enough to prevent the gas from collapsing into anything denser. The universe was in a kind of equilibrium, held open and uniform by the energy still bleeding off from recombination, gas too warm to collapse, too thin to shine, too structureless to become anything other than what it already was. But the universe was cooling. Every year that passed, the temperature dropped a little further, and as it dropped, the thermal pressure that was holding the gas smooth and uniform weakened. Gravity, which had been patiently waiting, began to gain the upper hand in certain regions, not everywhere, not all at once. The process was exquisitely sensitive to the initial conditions, to those tiny density variations that had been seeded in the first fractions of a second after the Big Bang. Where the gas was, by a tiny margin, denser than its surroundings, gravity pulled a little harder. Nearby, gas drifted almost imperceptibly toward those denser pockets. Over millions of years, the slightly denser regions became slightly denser still. The ocean was developing currents, invisible, slow, operating across distances of thousands and eventually millions of light-years, but real. The invisible ocean was beginning to stir. Here is something I find genuinely astonishing about this process. The density variations that were driving all of this, the initial seeds of every structure in the universe, were not large-scale features. They were not gross differences between one region and another that you could have detected by sampling the gas at two different locations. They were quantum fluctuations. Fluctuations that originated at subatomic scales in the first instant of the Big Bang, and were then stretched to cosmic scales by the rapid expansion of the early universe. The larger structures in the observable universe today, superclusters of galaxies stretching across hundreds of millions of light-years, were seeded by variations in density that, at their origin, existed at scales smaller than an atom. That connection between the quantum world and the cosmic world is not metaphorical. It is literal. The largest things that exist grew from the smallest possible variations in the earliest possible moment. As the cosmic dark age progressed and the gas continued to cool, the stirring of the invisible ocean became more pronounced. The filamentary structure that would eventually define the large-scale architecture of the universe, the vast cosmic web of gas and dark matter that connects galaxies like dew on a spider's web, was beginning to emerge from the smoothness. Long, thin tendrils of slightly denser gas were forming across distances of millions of light-years. Between them, regions of the gas were becoming emptier as matter drained away toward the filaments along gravity's invisible channels. The universe was developing texture. It was acquiring structure. Still dark, still cold, still utterly invisible to any eye or instrument that would have needed light to see. But physically, mathematically, irreversibly different from the smooth, featureless ocean it had been at recombination. At the densest nodes of this emerging web, where filaments intersected and matter accumulated from multiple directions simultaneously, the gas was beginning to do something new. It was beginning to pool, to concentrate, to form the protogalactic halos that would eventually become the birthplaces of the first stars. These halos were not yet stars, not yet anything we would recognize as a cosmic object. They were simply regions where the gas had become dense enough that gravity's grip was tightening measurably, where the long, slow process of collapse had begun in earnest, where the invisible ocean, over hundreds of millions of years of patient accumulation, had finally gathered enough matter in one place to begin the process of making something. I want you to hold the scale of this in your mind for a moment, even if only approximately. The invisible ocean stretched across the entire observable universe. The structures emerging within it spanned millions of light years. The process driving those structures operated over hundreds of millions of years. And the outcome of all that vastness, all that time, all that slow gravitational patience would eventually be a star. A single point of light perhaps a few hundred times the mass of our sun, igniting for the first time in the history of the cosmos. The ratio between the scale of the process and the scale of the outcome is almost incomprehensible. An ocean the size of the universe, stirring for 200 million years to light a single candle, and from that single candle eventually everything. Of all the forces that govern the universe, gravity is the one we understand best in our daily lives and yet comprehend least at cosmic scales. You feel it every moment of every day. It holds you to the ground, keeps the moon circling the earth, keeps the earth circling the sun. It is so familiar that we barely notice it. And yet gravity is, by a staggering margin, the weakest of the four fundamental forces. The electromagnetic force is roughly 10,000 trillion times stronger than gravity at the subatomic scale. The nuclear forces that hold atomic nuclei together are stronger still. Gravity is, in the language of physics, almost embarrassingly feeble. And yet gravity is the force that built every star, every galaxy, and every large-scale structure in the observable universe. It did it simply by never stopping, never switching off, never being screened or cancelled or neutralized by an opposing charge. Gravity always adds. And given enough time and enough matter, that relentless addition becomes something terrifying in its power. To understand how the first stars formed, you have to understand what gravity was working with during the cosmic dark age. The gas filling the universe was extraordinarily thin and cold and smooth. By any ordinary measure, there was almost nothing for gravity to grab onto. The density variations seeded by the Big Bang were at the level of roughly 1 part in 100,000. That means that the densest regions of the early universe were denser than their surroundings by a factor of about 0.001%. If you compressed the entire variation in the gas density of the early universe into a single image and looked at it, it would appear perfectly uniform to your eye. The differences were that small, and yet those differences were exactly what gravity needed. Because gravity is patient in a way that nothing in human experience can prepare you for. Here is the thing most people do not realize about gravitational collapse. It does not begin dramatically. It does not begin with a sudden implosion or a visible concentration of matter. It begins as a bias, a statistical lean, a region where, on average, over very large scales and very long times, slightly more matter is drifting inward than drifting outward. For millions of years, this bias is undetectable by any local measurement. The gas in a proto-collapsing region looks identical to the gas everywhere else. Same temperature, same density to any casual inspection, same featureless dark uniformity. But the numbers are tilting. Slowly, imperceptibly, the gravitational ledger is being written, and one side of it is accumulating a debt that will eventually have to be paid in the currency of collapse. The process that physicists use to describe this is called the Jeans instability, named after the British physicist James Jeans, who worked out the mathematics in the early 20th century. The core idea is elegant and rather simple. Any region of gas has two competing influences acting on it simultaneously. Gravity is trying to pull it together. Thermal pressure, the outward push of atoms moving with their heat energy, is trying to push it apart. As long as the thermal pressure is strong enough to resist the gravitational pull, the gas remains stable, it fluctuates, it moves, but it does not collapse into anything denser. But once a region of gas exceeds a certain critical size and density, which depends on its temperature and composition, gravity wins. The region becomes Jeans unstable, and once that threshold is crossed, the collapse becomes self-reinforcing. Denser gas pulls more strongly. Stronger pull brings more gas. More gas means higher density. The process accelerates, slowly at first and then with gathering speed, like a stone rolling down a hill that gets steeper as it descends. During the cosmic dark age, the gas was cooling steadily, and that cooling was critically important. Warmer gas has higher thermal pressure and is harder for gravity to collapse. As the universe expanded and the gas temperature dropped, the gene's mass, the minimum mass a gas cloud needed to become gravitationally unstable, was falling. The bar for collapse was getting lower. Regions of gas that had been stable at higher temperatures were approaching the threshold of instability. The cooling universe was, in a very real sense, preparing conditions for gravity to finally do what it had been unable to do in the hot, pressurized environment immediately after recombination. The dark, cold, expanding cosmos was inadvertently setting the stage for its own illumination. But cooling alone was not the whole story. Something else was helping gravity along. Something invisible, something we still do not fully understand, but whose gravitational influence we can measure with precision. Dark matter. This mysterious substance, which interacts with ordinary matter only through gravity, and which neither emits nor absorbs light, had been present since even before recombination. It had its own density variations, its own pattern of slight concentrations and slight voids, and those dark matter concentrations were acting as gravitational scaffolding for the ordinary hydrogen and helium gas. The gas was falling not just toward its own denser pockets, but toward the deeper gravitational wells created by invisible concentrations of dark matter distributed through the universe. Dark matter, despite being undetectable by any direct means we currently possess, was one of the primary architects of the first stars. Without it, the gas of the cosmic dark age might have taken much longer to collapse into anything. With it, the process had a head start, a set of pre-existing gravitational anchors around which ordinary matter could accumulate. There is a haunting quality to this picture that I keep returning to. The first whisper of gravity that would eventually lead to the first star was not dramatic. It was not a thunderclap or a sudden event you could have pointed to and said, "There, that is where it began." It was a gradient, a slope so gentle that it extended across thousands of light years, a statistical tendency encoded in the quantum fluctuations of the earliest universe, expressed through the patient mathematics of gravitational attraction, playing out over tens of millions of years in total darkness. The universe did not decide to make a star. It simply followed its own rules, consistently and without exception, across vast scales and vast times, until the rules inevitably produced one. And yet, knowing all of that, knowing the mechanism and the mathematics and the timeline, I still find myself struck by the improbability of it. The gas was so thin, the variations were so small, the forces were so feeble, the temperatures were so extreme. There were so many ways the balance could have tipped the other way, so many conditions that had to be met precisely for the first collapse to produce a star, rather than simply a slightly denser cloud of gas that would dissipate again over millions of years. The first whisper of gravity was quiet enough that it could easily have been drowned out. That it was not, that it grew instead into the roar of nuclear ignition, is not something the physics guarantees in all possible universes. It is something that happened in this one. And the fact that it happened, that gravity's first whisper eventually became a star, is the reason that anything else in this story is possible at all. Somewhere in the darkness, after 200 million years of cold and silence and patient gravitational accumulation, a cloud of hydrogen gas crossed a threshold that no cloud of gas had ever crossed before. It had been collapsing slowly, pulled inward by its own gravity, and by the deeper gravitational well of dark matter surrounding it, for millions of years. As it collapsed, it compressed. As it compressed, it heated. The atoms within it, which had been drifting in near isolation in the thin, cold gas of the cosmic dark age, were now being pushed together with increasing force and increasing frequency. The temperature at the core of the collapsing cloud climbed from the few dozen degrees above absolute zero of the surrounding gas to hundreds of degrees, then thousands, then tens of thousands, then millions. And then, at a core temperature of roughly 10 million degrees, something happened that had never happened before in the history of the universe. Two hydrogen nuclei, two lone protons, collided with enough force to overcome their mutual electromagnetic repulsion and fused together. The first nuclear reaction in any star had begun. The first light the universe had ever produced from a stellar source flooded outward into the surrounding dark. The cosmic dark age was over, and the star that ended it was like nothing that exists anywhere in the universe today. Astronomers classify stars into populations based on their chemical composition, specifically on how much of their mass consists of elements heavier than hydrogen and helium. These heavier elements are called metals in the language of astronomy, a usage that confuses many people because it includes things like carbon and oxygen that a chemist would not call metals at all. Our Sun is a population 1 star, meaning it contains a relatively high proportion of these heavier elements, about 2% of its mass. Older stars, born earlier in cosmic history when fewer heavy elements had been produced, are classified as population 2. They contain far less of these heavier elements, sometimes 100 times less than the Sun. But the very first stars, the ones born in the cosmic dark age from the primordial hydrogen and helium of the Big Bang, belong to a category that sits outside both of these. They are called population 3 stars, and not a single confirmed example of a population 3 star has ever been directly observed. They are, in the most literal sense, ghosts. Why have we never seen one? The answer is both simple and quietly devastating. Population. 3 stars were almost certainly enormous, and enormous stars die young. Our Sun, a modest and average star by cosmic standards, will live for roughly 10 billion years in total. Larger stars burn hotter and faster, consuming their fuel at a prodigious rate, and die in a fraction of the time. A star 10 times the mass of the Sun might live for only 20 million years before exploding as a supernova. A star 100 times the mass of the Sun might burn for only a few million years. Population 3 stars, according to our best models, were likely to have been extraordinarily massive, perhaps hundreds of times the mass of our Sun, and in some cases possibly even 1,000 times more massive. At those sizes, their lifespans would have been measured in millions of years at most. They were born, they burned with an almost incomprehensible ferocity, and they died, all within a cosmic eye blink. By the time the universe was old enough for anything we would recognize as a galaxy to form, the first generation of stars was already gone. But why were they so massive? This is one of the most fascinating questions in all of stellar astrophysics, and the answer lies in the unique conditions of the primordial universe. When a modern star forms, the gas cloud it collapses from contains not just hydrogen and helium, but traces of heavier elements, carbon, oxygen, silicon, and others forged in previous generations of stars. These heavier elements are extraordinarily efficient at radiating heat. When a gas cloud collapses and heats up, these elements absorb the thermal energy and radiate it away as infrared light, cooling the cloud and preventing it from building up too much pressure. This cooling effect allows modern molecular clouds to fragment into many smaller pieces, each of which becomes a relatively modest star. Our Sun formed this way, as one fragment among thousands from a collapsing molecular cloud. The primordial gas of the cosmic dark age had none of these cooling elements. It was pure hydrogen and helium, and these elements are comparatively poor radiators of heat. When a primordial gas cloud collapsed, the heat generated by compression had no efficient way to escape. The pressure built up rapidly, and the collapse stalled before the cloud could fragment. Instead of breaking into many small stars, the collapsing cloud tended to stay together as a single massive object, accumulating more and more mass before the core temperature finally reached the threshold for nuclear ignition. The result was a star of staggering proportions. Some models suggest that the very first stars may have reached masses of 300, 500, or even 1,000 times the mass of our Sun. Objects so extreme that nothing remotely like them exists in the observable universe today. Picture what such a star would look like if you could somehow be near enough to see it. It would be almost unimaginably bright. A star 100 times the mass of our Sun radiates not 100 times as much energy as the Sun, but roughly 1,000,000 times as much. A star of several hundred solar masses would outshine the Sun by a factor of billions. Its surface temperature would be far higher than the Sun's, pushing it deep into the ultraviolet and beyond. The light it emitted would be hard, energetic, ionizing radiation capable of stripping electrons from hydrogen atoms across enormous distances. A single population 3 star of sufficient mass would have been more luminous than an entire modern galaxy of hundreds of billions of ordinary stars. It would have been the most violent, most extreme, most brilliant object the universe had ever produced. And it would have been completely alone, burning in a darkness that had never known light before, surrounded by the cold gas of a universe that was only just beginning to wake up. These ghost stars left their mark in multiple ways. When they died violently. Stars above a certain mass threshold do not simply explode as supernovae and leave behind a neutron star or black hole the way smaller massive stars do. Some of the most extreme population 3 stars are thought to have undergone what physicists call a pair instability supernova, an explosion so total and so energetic that it left behind no remnant at all. The star simply annihilated itself in a blast that scattered its newly forged heavy elements, carbon, oxygen, silicon, iron, across enormous volumes of space. These were the very first heavy elements ever to exist freely in the universe. Forged in the cores of the ghost stars scattered by their deaths, they seeded the gas clouds that would eventually collapse into the next generation of stars, and the next, and the next. Until, billions of years later, a modest yellow star formed in an unremarkable spiral galaxy, orbited by a small rocky planet on which creatures made of those same ancient elements looked up at the night sky and wondered where they came from. There is a moment in the history of the cosmos that has no parallel. No event before it or after it quite compares to what happened when the first stars began to pour their radiation into the surrounding dark. Not the Big Bang itself, which was a transformation of pure energy into matter and space. Not the formation of the first atoms, which was a quiet chemical transition spread across the entire universe simultaneously. Not even the eventual formation of galaxies, which was a slow and gradual process extending over billions of years. The moment the first stars ignited and began to flood the universe with hard ultraviolet radiation was something categorically different. It was the universe catching fire. And the fire did not stop until it had transformed every cubic light-year of space across the entire observable cosmos. Scientists call this process the epoch of Rayonization, and it is one of the most violent, most total, and most consequential events in all of cosmic history. To understand what Rayonization was, you need to remember the state the universe was in just before it began. After a combination, 380,000 years after the Big Bang, the universe had become transparent. The plasma fog had cleared, the electrons had joined with protons to form neutral hydrogen atoms, and light could travel freely through space for the first time. But that neutral hydrogen, that vast invisible ocean of gas we explored in earlier chapters, had a particular property that would become critically important once the first stars ignited. Neutral hydrogen is very efficient at absorbing ultraviolet photons. When a photon of ultraviolet light from a hot young star encounters a neutral hydrogen atom, it does not simply pass through. It is absorbed, and the energy of that absorption is enough to knock the electron free from the proton again. The atom is ionized. It becomes a free proton and a free electron once more, just as it had been in the plasma of the early universe. Rayonization was, in the most literal sense, the universe being taken apart and rebuilt at the atomic level by starlight. The process began slowly. The very first stars were isolated, separated from each other by enormous distances across the primordial gas. Each one was surrounded by a growing bubble of ionized gas, a region where its ultraviolet radiation had stripped the surrounding hydrogen of its electrons. These bubbles are called Stromgren spheres, and in the early stages of Rayonization they were discrete, separate, floating in the still neutral sea of the cosmic dark age like bubbles of light expanding outward in an otherwise dark liquid. If you could have watched from a sufficient distance with instruments sensitive to the right wavelengths, you would have seen these bubbles appearing one by one across the dark universe, each one marking the location of a newborn star or cluster of stars, each one growing steadily outward as the radiation pushed further into the surrounding gas. The universe was developing patches of transparency within its vast neutral fog. Islands of Rayonized space, growing, expanding, not yet touching. But as more and more stars formed, as the first proto-galaxies began to coalesce and the rate of star formation accelerated, those bubbles grew larger. And then something decisive happened. The bubbles began to overlap. The edges of neighbouring ionized regions reached each other and merged, and the boundary between neutral and ionized gas began to shift from a collection of isolated spheres to something more like a continuous front sweeping outward across the universe. The timeline of this process is still a subject of active research, but our best current understanding suggests that reionization began somewhere around 150 million to 250 million years after the Big Bang, when the first stars ignited, and was substantially complete by around 1 billion years after the Big Bang. For roughly 800 million years, the universe was in the process of being reionized, its neutral hydrogen steadily consumed by the radiation of an accelerating population of stars and early galaxies. The energy involved in this transformation is almost impossible to convey. Every neutral hydrogen atom in the universe had to be ionized, which meant absorbing a photon energetic enough to free its electron. There are roughly 100 times more hydrogen atoms in the observable universe than there are grains of sand on every beach on Earth, and that comparison does not even begin to capture the real number. Every single one of those atoms, or very nearly so, was touched by this process. The total energy output of reionization, the sum of all the photons absorbed by all the hydrogen atoms across the entire observable universe over hundreds of millions of years, represents a scale of energetic transformation that dwarfs anything else that has happened in cosmic history since the Big Bang itself. And all of that energy came, ultimately, from the nuclear fires in the cores of the first generations of stars. Here is something that I find genuinely staggering about reionization, something that rarely gets mentioned when people talk about the history of the universe. After reionization was complete, the universe became transparent in a new and deeper sense than it had been after recombination. During the cosmic dark age, the universe was transparent to light in principle, but filled with neutral hydrogen that would absorb any ultraviolet photons almost immediately. After reionization, that barrier was gone. The intergalactic medium, the gas between galaxies, became a mostly ionized plasma through which ultraviolet and visible light could travel for billions of light years without significant absorption. The universe opened up. Light from the first galaxies could now cross the cosmos, and eventually, billions of years later, enter the instruments of our telescopes. Reionization was not just a physical transformation of the gas in the universe. It was the moment the universe became, in principle, observable across its full depth. And yet, despite this cosmic illumination, the process of reionization was in many ways terrifying for the gas clouds that were trying to form new stars. The same hard ultraviolet radiation that was ionizing the intergalactic medium was also heating it, dramatically. Gas that had been cool enough to collapse under gravity and form stars was suddenly being blasted by radiation that raised its temperature by tens of thousands of degrees. In many regions of the universe, this radiation heating was enough to completely suppress star formation, evaporating the gas that might have become the next generation of stars before it ever had the chance to collapse. Reionization was simultaneously creating the conditions for more stars and destroying the raw material that those stars would have needed. It was a feedback loop of extraordinary violence, playing out across the entire universe over hundreds of millions of years, and its details are still being worked out by astrophysicists today. We are living in the aftermath of that fire. The universe around us today, the transparent, ionized intergalactic medium through which galaxies peer at each other across billions of light years, is the direct legacy of reionization. Every observation we make of the distant universe, every photon that has travelled for 12 or 13 billion years to reach our detectors, has passed through gas that was transformed by the first stars. The light we see from the most distant galaxies is ancient enough that it was emitted during or just after reionization. When we look at the edge of the observable universe, we are looking at the embers of the fire that the first stars lit. And somewhere, just beyond the reach of even our most powerful instruments, in the darkness just before those first stars ignited, lies the cosmic dark age. Silent, cold, waiting, as it always was, just out of sight. Take a breath. Right now, as you listen to this, draw a slow breath in and let it fill your lungs. That breath contains oxygen, the element that makes it possible for your blood to carry energy to every cell in your body. The air around you contains nitrogen, carbon dioxide, and traces of dozens of other substances. Your body itself is a catalogue of elements: carbon in your DNA and your proteins, calcium in your bones, iron in your blood, phosphorus in your cells, sodium and potassium humming through your nerve endings with every thought you have. You are, in the most literal chemical sense, a collaboration between roughly 25 different elements. And here is the thing that should stop you in your tracks, at least for a moment, on a quiet night, when you have the space to really feel it. Not one of those elements existed anywhere in the universe before the first stars were born. The cosmos, for the first 200 million years of its existence, was chemically almost empty. The periodic table contains 118 confirmed elements. Of those 118, exactly 3 existed in any significant quantity before the first stars ignited. Hydrogen, the simplest and most abundant, a single proton orbited by a single electron. Helium, 2 protons and 2 electrons, chemically inert and extraordinarily stable, and trace amounts of lithium, produced in minuscule quantities during the brief window of Big Bang nucleosynthesis. That is it. 3 elements. Everything else, every element from beryllium at number 4 all the way to the heavier synthetic elements at the end of the table, did not exist in any meaningful quantity anywhere in the observable universe. The cosmos had a chemistry so impoverished that it barely deserved the name. It was a universe of hydrogen and helium, and almost nothing more. This is not a minor gap in the early universe's resume. Consider what is missing when a cosmos contains only those 2 lightest elements. There is no carbon, whose unique capacity to form long and stable molecular chains makes the chemistry of life possible. There is no oxygen, without which no water can form and no aerobic metabolism can occur. There is no nitrogen, no phosphorus, no sulfur, none of the elements that build proteins and DNA, and the membranes of living cells. There is no silicon to form the rocky crusts of planets. There is no iron to form planetary cores or carry oxygen through blood. A universe of hydrogen and helium is a universe where planets as we know them cannot exist, where liquid water is impossible, where organic chemistry cannot begin, and where life in any form resembling what we know is simply not an option. The pre-stellar universe was not just dark and cold. It was, in a deep and chemical sense, sterile. So where did all the other elements come from? The answer is the interior of stars, and specifically the nuclear fusion process that powers them. When a star ignites and its core reaches the temperatures needed for hydrogen to fuse into helium, it is performing a kind of alchemy that the Big Bang could not accomplish at scale. It is building heavier atomic nuclei from lighter ones, adding protons and neutrons and creating elements that did not previously exist in any significant abundance. In a star like our Sun, the primary process converts hydrogen to helium throughout the star's long main sequence lifetime. But in larger and hotter stars, once the hydrogen in the core is exhausted, the core contracts and heats further until temperatures are reached at which helium nuclei themselves begin to fuse, forming carbon. Then carbon fuses to oxygen, oxygen to neon, neon to magnesium, and the sequence continues, each step requiring higher temperatures, each step producing a heavier element, climbing the periodic table rung by rung through the nuclear fires at the heart of a dying giant. The most massive stars can run this entire fusion sequence all the way to iron. Iron occupies a special and rather melancholy position in the story of how elements are made. It is the element with the most stable nucleus of all, the one that releases no net energy when fused into something heavier. When a massive star's core fills with iron, the fusion process that has been generating the outward pressure holding the star against gravity simply stops. Without that pressure, the core collapses in a fraction of a second, triggering a supernova explosion so energetic that it briefly outshines an entire galaxy. And in the outer layers of that explosion, in the ferocious heat and pressure of the shockwave, elements heavier than iron are forged. Gold, silver, platinum, uranium, lead. Every heavy element you have ever held was created in the death of a massive star and scattered into space by that death, to drift in the interstellar medium for millions or billions of years until gravity gathered it again into the next generation of stars and planets. The first generation of Population 3 stars was therefore not just the first light in the universe. It was the first forge, the first chemical laboratory the cosmos had ever had. Those enormous short-lived ghost stars took the hydrogen and helium of the primordial universe and began, for the first time in history, to build the periodic table. When they died in catastrophic explosions, they scattered the first carbon, the first oxygen, the first silicon, the first iron into the gas clouds around them. Those enriched clouds eventually collapsed into the second generation of stars, which were themselves enriched by the first, and which in turn enriched the gas clouds they would leave behind. Generation after generation, the universe's chemistry deepened. The proportion of heavy elements in the interstellar medium grew, slowly and steadily, as successive generations of stars lived and died, and returned their newly forged elements to the cosmos. There is a timeline embedded in this process that should genuinely astonish you. The first population 3 stars almost certainly formed within the first 200 to 400 million years after the Big Bang. They lived for perhaps a few million years. When they died, their supernovae seeded the surrounding gas with the first heavy elements the universe had ever known. Those first heavy elements scattered into space in the earliest galaxies were already present when the universe was less than 1 billion years old. The carbon and oxygen that would eventually find their way into living cells on Earth were being manufactured in stellar cores and scattered by supernovae billions of years before the Earth even existed, before our solar system, before our galaxy had taken its current shape. The raw materials of life were being produced almost from the very beginning, carried forward through generation after generation of stars, waiting across unimaginable spans of time for the right conditions to assemble them into something that could breathe. I want you to feel the weight of that chain for a moment before we move on. Every atom in your body has a history that stretches back to a star. Not necessarily one star, and not our Sun, which is not hot enough to have forged anything heavier than helium in its core. The carbon in your DNA was forged in the core of a star that died before our solar system was born. The iron in your blood was created in the heart of a massive star that exploded billions of years ago. The calcium in your bones was scattered into space by a supernova whose light no living eye ever saw. You're not just connected to the stars in a poetic sense. You are the stars, reassembled. You are the product of a universe that spent 200 million years in chemical poverty before the first fires finally began to build the elements that would, eventually and inevitably, become you. There is something in the universe that we cannot see, cannot touch, cannot detect with any instrument we have ever built that responds to light. It does not emit radiation. It does not absorb radiation. It does not reflect or scatter or interact with photons in any way that our telescopes can measure. And yet we know it is there, with a confidence that physicists rarely have about anything so invisible, because its gravitational influence on everything around it is measurable, consistent, and impossible to explain away. We call it dark matter, and here is the part of the story that most people never hear, the part that changes how the entire pre-stellar universe looks when you know it. Dark matter was not something that appeared later in cosmic history. It was not a secondary feature added to the universe after the first stars. It was there before the first star. It was there before the first atom. It was there in the cosmic dark age, in the invisible ocean, permeating the primordial gas and shaping its future from the very beginning. The universe we think we understand, made of atoms and light and chemistry, is a minority. Dark matter makes up roughly 27% of everything the universe contains, and it has been the dominant structural force in the cosmos since the very first moments of existence. Let me be precise about what dark matter is not, because the misconceptions are almost as interesting as the reality. It is not dark energy, which is a separate and even more mysterious component of the universe that we will visit in a later chapter. It is not a cloud of black holes, at least not entirely. It is not antimatter, which would annihilate with regular matter and produce a detectable burst of gamma rays. It is not some exotic form of gas that we have simply failed to detect with current instruments. Dark matter is something genuinely different from all the ordinary matter in the universe, matter made of protons, neutrons and electrons, the stuff that forms atoms, molecules, stars, planets and you. The leading hypothesis among physicists is that dark matter is made of a type of particle, or perhaps several types, that interact with ordinary matter only through gravity and possibly through the weak nuclear force, but not through electromagnetism at all. Because electromagnetism is the force that produces light in all its forms, a particle that does not interact electromagnetically is, by definition, invisible to every optical, radio, infrared, ultraviolet, and X-ray telescope ever built. The evidence for dark matter's existence is overwhelming and comes from many independent directions simultaneously. When astronomers measure how fast stars orbit the centres of galaxies, including our own Milky Way, they find that the outer stars are moving far too fast. Based on the visible mass of the galaxy, the stars at the edges should be moving much more slowly, just as the outer planets in our solar system move more slowly than the inner ones. But they are not slow. They are moving at speeds that, if the visible mass of the galaxy were all the mass there was, would cause them to fly off into intergalactic space. Something is holding them in. Something with mass and therefore gravity, distributed through and around the galaxy in a vast invisible halo extending far beyond the visible disk of stars. That something is dark matter. The same conclusion is reached when astronomers study clusters of galaxies, when they measure the bending of light by gravitational lensing, when they model the large-scale structure of the universe. Everywhere they look, with every independent method they apply, the answer is the same. There is far more matter than we can see, and there always has been. During the cosmic dark age, dark matter was not a passive bystander. It was an architect. Because dark matter responds to gravity, but not to the thermal pressure that ordinary gas experiences, it began forming structures earlier and more efficiently than ordinary hydrogen and helium could. While the primordial gas was still warm enough that its thermal pressure resisted gravitational collapse, dark matter was already clumping together under gravity into the halos and filaments and sheets that would eventually define the large-scale structure of the cosmos. These dark matter structures formed first, and then ordinary matter fell into them. The gas of the cosmic dark age did not collapse randomly into stars and galaxies wherever its own density variations happened to be slightly higher. It collapsed preferentially into the gravitational wells that dark matter had already dug, following invisible scaffolding that dark matter had constructed in the dark, across vast distances over hundreds of millions of years. Think about what this means for the story of the first stars. The regions of primordial gas that would eventually collapse and ignite were not chosen purely by the random fluctuations in the gas itself. They were guided, pre-selected in a sense, by the deeper gravitational architecture of dark matter halos that had been forming and growing since before recombination. The first stars did not appear at arbitrary locations in the universe. They appeared at the nodes and intersections of a dark matter web that was already billions of times more structured than the gas it was invisibly organizing. The cosmic dark age was not just a story of hydrogen and helium drifting and cooling. It was a story of two parallel universes, one made of ordinary matter that we can see, and one made of dark matter that we cannot, interacting only through gravity, each shaping the destiny of the other across the full 200 million years of prestellar darkness. Here is something that I find genuinely unsettling about this picture, in the best possible sense. We have never directly detected a dark matter particle. Not once. Not in any laboratory, not with any purpose-built detector, despite decades of increasingly sensitive experiments specifically designed to catch the faintest possible signal of a dark matter particle interacting with ordinary matter. The largest and most sensitive dark matter detectors on Earth, buried deep underground to shield them from cosmic ray interference, have so far returned only silence. We know dark matter is there from its gravitational effects. We can map its distribution across the universe through the bending of light and the motion of galaxies. We can simulate its behavior with extraordinary precision and match those simulations to observations. But what it actually is, what particle or particles make it up, remains one of the deepest unsolved problems in all of physics. The dominant structural component of the universe, the scaffolding on which every galaxy and every star was built, remains fundamentally unidentified. And it was there before the first star, before the first atom technically, since dark matter does not form atoms. It was present in the earliest instance of the Big Bang, falling out of the primordial plasma as the universe cooled, clumping under gravity in the darkness before anything else had taken shape. When you picture the cosmic dark age, that vast invisible ocean of hydrogen and helium drifting in the dark, you now need to add another layer to that picture. Running through it, coexisting with it but invisible even in principle, was a dark matter structure of extraordinary complexity. Filaments and sheets and halos of invisible mass, exerting their gravitational influence on the gas around them, shaping its future without touching it in any way we can directly observe. The darkness before the first star was not simple, it was layered, it was structured. It was already, in the geometry of dark matter, beginning to look faintly like the universe we know. We just could not have seen any of it, even if we had been there to look. In the year 1964, two American radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna in New Jersey, trying to eliminate a persistent and inexplicable noise from their instrument. The noise was faint, uniform, and maddeningly constant. It came from every direction in the sky with equal intensity. They checked their equipment repeatedly. They recalibrated their antenna. They even cleaned out a pair of pigeons that had nested inside the horn and removed what they politely described in their scientific paper as a white dielectric material, which is a very careful way of saying pigeon droppings. Nothing helped. The noise persisted. What Penzias and Wilson had stumbled onto, without fully realizing it at first, was the oldest light in the observable universe. A faint glow of microwave radiation filling the entire sky in every direction. The direct fossil remnant of the moment 380,000 years after the Big Bang, when the universe first became transparent. They called it noise. History calls it the cosmic microwave background, and it is our most direct window into the era before the first star ever existed. To understand what the cosmic microwave background is, you need to remember what happened at recombination. Before that moment, the universe was an opaque plasma, a dense fog of charged particles through which light could not travel freely. Photons were constantly being absorbed and re-emitted, trapped in the plasma like light bouncing around inside a thick cloud. Then, as the universe expanded and cooled to roughly 3,000 degrees, electrons slowed down enough to be captured by protons, forming the first neutral hydrogen atoms. The fog cleared almost instantaneously, in cosmic terms. And the photons that had been trapped in the plasma for 380,000 years were suddenly free to travel. They streamed outward in every direction, filling the newly transparent universe with light. That light has been travelling ever since. For 13.4 billion years, those photons have been crossing the expanding universe, being stretched by the expansion to longer and longer wavelengths, cooling from the infrared glow of 3,000 degrees all the way down to the microwave frequencies they occupy today. The faint microwave glow that Penzias and Wilson detected was those same photons, finally arriving at Earth after a journey of almost the entire age of the universe. The cosmic microwave background is not just a historical curiosity, it is a map. A precise, detailed, extraordinarily information-rich map of the state of the universe at the moment of recombination, which means it is also a map of the conditions that produced the cosmic dark age that followed. Because the photons released at recombination carry the imprint of the plasma they were trapped in, the tiny temperature variations encoded in them reflect the density variations in the primordial gas at that moment. The slightly hotter spots in the map correspond to regions where the gas was slightly denser. The slightly cooler spots correspond to regions that were slightly emptier. These variations are small, roughly 1 part in 100,000, but they are real and they are measurable. And they are the same density variations that gravity would spend the next 200 million years amplifying into the first stars and galaxies. The cosmic microwave background is not just a picture of the past. It is the blueprint from which the entire large-scale structure of the universe was constructed. In 1989, NASA launched a satellite called the Cosmic Background Explorer, known as COBE, specifically designed to measure the cosmic microwave background with unprecedented precision. What COBE found earned its principal investigators the Nobel Prize in Physics. The background radiation was not perfectly uniform. It had the tiny temperature fluctuations that cosmologists had predicted must be there, based on the theory that structure in the universe grew from small initial density variations. Those fluctuations, at roughly 100,000th of a degree in amplitude, were exactly what the models required. They confirmed that the universe we live in, with its galaxies and clusters of galaxies and vast cosmic web of structure, grew from precisely the kind of small initial perturbations that the physics of the early universe predicted. COBE was followed by more precise satellites DubMap and then Planck, each mapping the cosmic microwave background in greater detail, and the picture that emerged was one of the greatest triumphs of scientific measurement in history. The universe, in its earliest observable state, matched theory with extraordinary precision. But here is what I want you to really sit with about the cosmic microwave background. When you look at a map of it, those beautiful oval projections of the full sky covered in faint blue and red patches marking slightly cooler and slightly warmer regions, You're not looking at something abstract or theoretical. You're looking at actual light that left the surface of last scattering 13.4 billion years ago. Photons that have been travelling through the expanding universe since before the first star existed, since before the cosmic dark age had even properly begun. Those photons were released when the universe was 380,000 years old, an almost incomprehensibly small fraction of its current age. They predate the first star by roughly 200 million years. They predate the Earth by 9 billion years. They predate every living thing that has ever existed on this planet by more than 9 billion years. And they arrived at our instruments still carrying their ancient information, patient and unchanged in their fundamental nature despite their 13 billion year journey. There is a boundary embedded in the cosmic microwave background that has a name physicists sometimes call the surface of last scattering. It is the farthest back in time that any photon of light can ever carry information to us. Before that surface, the universe was opaque. The plasma fog absorbed all light instantly. Nothing from earlier than 380,000 years after the Big Bang can ever reach us as a photon of electromagnetic radiation, no matter how powerful a telescope we build. The cosmic dark age, the era of the first stars, the epoch of reionization, all of these took place after the surface of last scattering, and in principle we can observe them through their effects on the light that passed through them. But the plasma era and the Big Bang itself, and whatever came before, are permanently screened from optical observation by that wall of opacity. The cosmic microwave background is not just the oldest light we can see, it is the oldest light we will ever be able to see. And yet even that boundary is not the end of what we can learn, because the cosmic microwave background is not the only fossil of the early universe. Gravitational waves, ripples in the fabric of space-time itself, can in principle pass through the plasma era unimpeded. They do not interact with matter the way photons do. A sufficiently powerful gravitational wave detector, perhaps one operating in space rather than on the ground, might one day be able to detect the faint gravitational wave background produced in the first fractions of a second after the Big Bang, carrying information from before the surface of last scattering, from the very earliest moments of existence. We have not built that detector yet, but the possibility exists. The cosmic microwave background opened a window onto the pre-stellar universe that changed everything we thought we knew. And somewhere beyond it, in a whisper of space-time rather than a whisper of light, the universe may yet have more ancient secrets waiting to be heard. On the 18th of December, 2021, a rocket lifted off from a launch pad in French Guiana, carrying the most ambitious and expensive scientific instrument humanity had ever built. The James Webb Space Telescope had been in development for over 2 decades. It had cost approximately $10 billion. It had involved the work of thousands of scientists, engineers, and technicians across multiple countries and multiple generations of careers. It had been delayed, redesigned, and rescheduled so many times that the joke in the astronomical community was that Webb would launch sometime between always and never. And when it finally did launch, when it finally unfolded its golden hexagonal mirror in the cold of space and reached its operational position 1.5 million kilometers from Earth, it began returning images that changed the way we understand the early universe. Some of what it found confirmed our models beautifully, and some of what it found was deeply, uncomfortably shocking. To appreciate what Webb can do that no previous telescope could, you need to understand something about how looking into space is the same as looking back in time. Light travels fast, roughly 300,000 kilometers per second, but the universe is vast enough that even at that speed, the light from distant objects takes enormous amounts of time to reach us. The light from our sun takes about 8 minutes to arrive. The light from the nearest star takes over 4 years. The light from the Andromeda Galaxy, the nearest large galaxy to our own, takes 2.5 million years. And the light from the most distant galaxies we can observe left its source over 13 billion years ago, when the universe was less than 1 billion years old. When we observe those distant galaxies, we're not seeing them as they are now. We're seeing them as they were billions of years ago, when the universe was young. Every powerful telescope is also, in a very real sense, a time machine. The Hubble Space Telescope, which launched in 1990 and transformed our understanding of the cosmos over its long operational lifetime, could see galaxies as far back as about 13 billion years, when the universe was roughly 800 million years old. That was extraordinary. but it was not far enough to reach the epoch of reionization, or the era of the first stars. Webb was designed to go further. Its mirror is nearly 3 times the diameter of Hubble's, giving it vastly more light-gathering power, and crucially it was optimized for infrared wavelengths of light rather than visible light. This matters enormously because of a phenomenon called cosmological redshift. As the universe expands, the wavelengths of light travelling through it are stretched. Light that was emitted as visible or ultraviolet radiation by ancient galaxies has been stretched over billions of years of cosmic expansion into infrared wavelengths by the time it reaches us. Hubble, operating primarily in visible light, simply could not detect that ancient infrared glow. Webb can. And what Webb found when it pointed at the oldest, most distant regions of the sky was both magnificent and deeply unsettling. Within the first months of its scientific operations, Webb detected galaxies at distances corresponding to redshifts that placed them within the first few 100 million years of cosmic history. Galaxies seen as they were when the universe was only 300 million years old. Some of them, shockingly, were not the small, irregular, primitive proto-galaxies that our models had predicted would exist at such early times. They were large, surprisingly, disturbingly large. Several of the early galaxies Webb detected had stellar masses comparable to, or even exceeding those of galaxies in the modern universe. Galaxies that by our standard models of galaxy formation should have taken billions of years to accumulate that much stellar mass. They appeared far too early, far too developed, far too massive for the timeline our models predicted. When early results were announced, some cosmologists used phrases in their papers that are rarely seen in scientific literature. Phrases like impossible galaxies, galaxies that should not exist at those distances, at that epoch, given our current understanding of how structures form and grow in the universe. Here is the thing most people do not realize about what these early Webb findings mean. They do not necessarily mean our fundamental cosmology is wrong. The Big Bang model, the expansion of the universe, the formation of hydrogen and helium in the first minutes, the cosmic dark age, the existence of dark matter, all of these remain on extraordinarily solid observational footing. What the early Webb galaxies suggest is that something about the details of galaxy formation in the early universe is not captured by our current models. Perhaps star formation in the early universe was more efficient than we thought, converting gas into stars at higher rates. Perhaps the dark matter halos that seeded the first galaxies were structured differently than our simulations assume. Perhaps the first population 3 stars were so massive and so luminous that they triggered a cascade of star formation that built large galaxies far faster than anything that happens in the universe today. We do not yet know. And that uncertainty is not a failure of science. It is science doing exactly what it is supposed to do, encountering the unexpected and being forced to grow. Beyond the surprise of massive early galaxies, Webb has also begun to probe the epoch of reionization directly in ways Hubble never could. By studying the spectra of very distant quasars, enormously luminous objects powered by supermassive black holes in the centers of early galaxies, Webb can measure how much neutral hydrogen exists between us and those quasars along the line of sight. Neutral hydrogen absorbs specific wavelengths of light in a characteristic way, and by mapping those absorptions across different distances and directions, astronomers can build a picture of when and how the neutral hydrogen fog of the cosmic dark age was progressively burned away by the radiation of the first stars and galaxies. Webb is, in effect, watching the epoch of reionization happen in real time across the sky, tracing the progress of the fire that ended the cosmic dark from multiple angles simultaneously. And then there is what Webb has not yet found, the target that remains just beyond its reach, the very first stars, the population 3 ghost stars that ended the cosmic dark age. Webb can, in principle, detect the signatures of these stars in certain ways, through the specific pattern of light emitted by very hot, very massive metal-free stars, a pattern different enough from normal stellar populations that it should be distinguishable. There are candidate observations, hints in the spectra of certain early galaxies that might indicate the presence of population 3 stars or their immediate descendants. But a confirmed, unambiguous direct detection of a population 3 star or cluster has not yet been achieved. They burned too briefly, too far away, too long ago. The edge of what Webb can see is tantalizingly close to the era of the first stars, but the first stars themselves remain for now just out of reach. A shadow at the edge of the observable universe, present in the physics, implied by everything we know, but not yet directly seen. The ghost stars keep their secret a little longer, but Webb is looking, and every day it looks, it sees further into the dark. We have travelled a long way tonight. We began in the darkness before the first star, moved through the cosmic dark age, watched the first fires ignite, traced the elements being forged, followed the light of reionization spreading across the cosmos, and looked through the most powerful telescope humanity has ever built toward the edge of what is observable. But there is one more step I want to take with you. One more door I want to open, even though what lies behind it is not a room with walls and a floor and a ceiling, but something far stranger. Something that physics approaches with extraordinary caution and genuine humility. The question of what came before the Big Bang. The question of what, if anything, existed before the universe began. And the deeply unsettling possibility that this question may not just be unanswered, but may be, in a fundamental and permanent sense, unanswerable. Let us start with what we mean by before. In everyday life, before is a simple concept. Before breakfast comes sleep. Before yesterday comes the day before that. Time, in our experience, is a line stretching backward into the past without any obvious limit. You can always ask what happened before any given event and expect that something did in fact happen. The question makes sense. It has a meaningful answer. But here is where the physics becomes terrifying in its strangeness. Time, according to our best understanding of general relativity, is not a fixed background against which events occur. It is a dimension of space-time, woven together with the three spatial dimensions into a single four-dimensional fabric that is shaped by the matter and energy it contains. And at the Big Bang, according to general relativity, the curvature of that fabric becomes infinite. The equations break down completely. The concepts of before and after, of earlier and later, lose their meaning in the same way that the concept of north loses its meaning when you're standing at the North Pole. If time itself began at the Big Bang, then asking what came before is like asking what is north of the North Pole. The question sounds grammatically sensible, but it may have no physical content at all. This was the insight that the physicist Stephen Hawking and the cosmologist James Hartle explored in their no-boundary proposal in 1983. In their model, the universe has no boundary in time, no initial moment beyond which you can ask what came before, because time near the Big Bang behaves more like a spatial dimension than a temporal one. The beginning of the universe in this framework is not a wall you hit when you go back far enough. It is more like the surface of a sphere. If you travel southward on the surface of the Earth, you do not eventually reach a wall or an edge. You reach the South Pole, and then the concept of southward simply stops applying. In the Hartle-Hawking model, the same thing happens with time at the Big Bang. It does not end at a wall, it rounds off smoothly. And the question of what came before simply stops applying, not because something is hidden, but because the question itself is malformed. But not all physicists accept this framework, and there are alternative pictures of cosmic origins that take the question of before seriously and attempt to give it an answer. In the theory of eternal inflation, proposed by the physicist Andrei Linde among others, our universe is not the whole story. It is one bubble in an eternally inflating multiverse, a vast and perhaps infinite sea of rapidly expanding space in which individual universes nucleate randomly, like bubbles forming in a boiling liquid. In this picture, our Big Bang was not the beginning of everything. It was a local event, the moment one bubble of slow-roll inflation came into being within a larger inflationary background that has always existed and always will exist. Before our Big Bang, in this framework, there was the multiverse, and the multiverse had no beginning either, extending infinitely into the past in a state of perpetual rapid expansion from which other universes, other bubbles, were constantly being born. There are other proposals as well. The cyclic cosmology developed by Paul Steinhardt and Neil Turok suggests that our universe is one phase in an endless cycle of expansion and contraction, with Big Bangs not as absolute beginnings, but as transitions between phases, our universe bouncing out of the collapse of a previous one. Loop quantum cosmology, which applies the mathematics of quantum gravity to the Big Bang singularity, finds that the singularity dissolves in their framework, replaced by a big bounce in which a previous collapsing universe reached a minimum size and rebounded into expansion. In each of these proposals, there is something before our Big Bang. Something existed. Something happened. The question has an answer, even if we cannot yet confirm what that answer is. Here is the thing most people do not realize about all of these proposals, and it is important enough that I want to say it carefully. Every single one of them, the no-boundary model, eternal inflation, cyclic cosmology, loop quantum cosmology, every framework that attempts to address what came before the Big Bang makes predictions that are either untestable with any technology we currently possess, or that we have not yet found a way to distinguish from competing models observationally. They are not arbitrary speculation. They are built on rigorous mathematics and are consistent with everything we know about physics, but they are not yet confirmed science in the way that the Big Bang model itself is confirmed science. The cosmic microwave background, the abundances of light elements, the expansion of the universe, these are hard, direct observational evidence for the Big Bang. Evidence for what came before the Big Bang, if anything did, remains elusive, indirect, and deeply contested among experts. And this is where I want to pause for a moment, because there is something philosophically profound in this situation that goes beyond the technical details. We are creatures who evolved on a small planet orbiting an ordinary star, equipped with brains that developed to solve problems of survival on the African savanna over a span of millions of years. And yet those same brains have built instruments sensitive enough to detect the oldest light in the universe, have developed mathematics powerful enough to describe the first fractions of a second of cosmic time, and have arrived at the boundary of a question that may lie permanently beyond the reach of any possible observation. The question of what came before the universe may be the first question in human history that is not just currently unanswered, but may be structurally unanswerable. Not because we're not clever enough, but because the universe itself may not contain the evidence needed to answer it. There is a strange comfort in that, if you let yourself feel it. We are small, we are brief. We appeared in the universe billions of years after the first star and will be gone, in cosmic terms, almost instantly. And yet we have pushed our understanding all the way back to the first fractions of a second after the beginning of everything, and we have arrived at the edge of the knowable with our curiosity still burning. We have not turned back from the question just because it is hard. We have not decided that the answer does not matter because it does not affect our daily lives. We have kept asking. We have kept looking. We have built better instruments and developed more powerful mathematics and argued with each other across decades about what it all means. The question no one can answer is not a failure. It is the horizon toward which every generation of curious minds has been walking, and horizons, by their nature, keep moving as you walk toward them. You have heard the phrase before, you're made of stardust. It is one of those ideas that gets repeated so often in popular science that it has lost some of its power, worn smooth by familiarity until it feels more like a poetic slogan than a statement of physical fact. But tonight I want to take it apart and put it back together again, carefully and slowly, because the reality behind that phrase is so much more specific, so much more traceable, and so much more astonishing than the bumper sticker version suggests. And then I want to take one step further back than the phrase ever goes. Because if you are made of stardust, if your atoms were forged in stellar cores and scattered by supernovae, then the question that naturally follows is this: what made the stars? And the answer to that question leads us all the way back to the darkness before the first light, back to the cold hydrogen ocean of the cosmic dark age, and further still, back to the quantum fluctuations of the earliest universe, until the chain of your own origin stretches across 13.8 billion years and touches the very first moments of existence. Let us trace it carefully. The oxygen in your lungs right now, the oxygen your blood is carrying to your brain as you listen to this, was forged in the core of a star. Not our sun, which is not hot enough to fuse anything heavier than helium in its core during its normal lifetime. A different star, one larger and hotter than the sun, which lived and died billions of years before our solar system formed. In that star's core, helium nuclei fused together to form carbon, and then carbon and helium fused to form oxygen, and that oxygen was locked inside the star for millions of years, until the star exhausted its nuclear fuel, collapsed, and exploded in a supernova that scattered its outer layers across the surrounding interstellar medium. The oxygen travelled, it mixed with other gas, it drifted through the galaxy for millions or billions of years. Eventually some of it was swept up in the collapsing cloud of gas and dust that would become our solar system, incorporated into the rocky material of the forming Earth, cycled through geological and atmospheric processes over billions of years, and ended up, eventually, as part of the air you're breathing right now. Every breath is an act of cosmic archaeology. The carbon in your DNA has a similar story. forged in stellar cores through the triple alpha process, a remarkable nuclear reaction in which 3 helium nuclei collide and fuse to form a single carbon nucleus. This process requires a very specific resonance in the energy levels of carbon, a coincidence so precise that the physicist Fred Hoyle predicted it must exist before it was experimentally confirmed, reasoning that if it did not exist, carbon could not be produced in stars, and since we exist and are made of carbon, it must be there. It was. The carbon in your body traces back to stars that lived and died before the sun was born, their cores running the triple alpha process for millions of years, building up carbon that was then scattered by their deaths and eventually incorporated into the chemistry of our solar system, and, billions of years later, into the molecules of life. The iron in your blood was forged in the cores of the most massive stars, at the end of their lives when silicon burning produced iron in the final hours, before gravitational collapse triggered a supernova. The calcium in your bones was produced in supernova, scattered across the galaxy, incorporated into dust grains and then into the rocky body of the early Earth. You're not made of one star's worth of material. You're a mosaic of elements from many different stars, from many different generations of stellar evolution, from many different locations in the galaxy, brought together by the extraordinary accident of the solar system's formation from a particularly well-enriched cloud of interstellar gas. The atoms in your left hand and the atoms in your right hand may have come from completely different stellar sources, forged in stars that never interacted with each other, that lived and died in different parts of the galaxy, that existed at different points in cosmic history. You are a collaboration between stars that never knew each other, and the meeting point for all of their contributions was a collapsing gas cloud 4.6 billion years ago that happened to be in the right place at the right time in the chemical history of the Milky Way. But now take the step that the Stardust story usually skips. If your atoms were forged in stars, what made the stars? The stars formed from clouds of gas, predominantly hydrogen and helium, that collapsed under gravity in the interstellar medium. That gas was not created by the stars, it predates them. It is the primordial hydrogen and helium of the Big Bang nucleosynthesis, the same gas that filled the cosmic dark age, the same invisible ocean we have been exploring all night. The hydrogen in your body, every hydrogen atom in every water molecule in every cell, was not made in a star. It is primordial, it is original. It dates back to the first 3 minutes of the universe, when protons formed from the quark-gluon plasma of the Big Bang and were never subsequently destroyed. The hydrogen atoms in you are 13.8 billion years old. They are as old as the universe itself. They have been part of the cosmic story from the very beginning, drifting through the cosmic dark age as part of the primordial gas, swept up into stars that later died and scattered their heavier elements, eventually finding their way into you. And if you trace the hydrogen back further still, you arrive at the quarks. The protons that make up the hydrogen nuclei in your body are each composed of 3 quarks, bound together by the strong nuclear force. Those quarks condensed out of the quark-gluon plasma of the very early universe in the first microsecond after the Big Bang, when the universe had cooled enough for quarks to combine into protons and neutrons. Before that, the quarks themselves existed as free particles in the plasma, indistinguishable from the general energy of the cosmos. And before that, in the first fractions of a second after the Big Bang, there were no quarks yet, only energy in its most primordial form, the undifferentiated fire of the singularity. You trace back to that too. Every particle in you is a descendant of that original energy, transformed through successive stages of cosmic cooling and chemical enrichment into the extraordinary complexity of a living, breathing, conscious human being. Here is what I want you to carry with you from this chapter as you drift towards sleep tonight. The chain of your origin is unbroken. There is no gap in the sequence, no moment where something came from nothing or where the story loses continuity. From the quantum fluctuations of the earliest universe, to the primordial gas of the cosmic dark age, to the first stars, to their deaths and the scattering of heavy elements, to the enrichment of the interstellar medium across generations, to the formation of our solar system and our planet, to the chemistry of life and the long, slow process of biological evolution, the thread runs continuously and without interruption. You're not separate from the cosmos. You're not a visitor to the universe who arrived from somewhere else. You are a local expression of a process that began 13.8 billion years ago in total darkness and has been building, one step at a time, toward ever greater complexity, ever greater structure, ever greater awareness. The darkness before the first star was not the absence of you, it was the beginning of you. It just took the universe a very long time to figure out what it was making. There is a version of this story that ends before it begins. A universe that expanded from the Big Bang just as ours did, that produced hydrogen and helium in its first 3 minutes just as ours did, that cooled and darkened into a cosmic dark age just as ours did, and then stayed dark. Forever. A universe in which the conditions were almost right for stars but not quite, in which the balance of forces and constants and initial densities fell just slightly outside the narrow range required for gravity to win its long, slow battle against pressure and radiation. A universe of permanent, silent, lightless gas, expanding forever into a cold and structureless eternity, with no stars, no planets, no chemistry beyond the simplest, and no possibility of anything like life or awareness or the asking of questions about where it all came from. That universe did not happen. But it almost did, and understanding how close it came, how razor-thin the margin was between the cosmos we have and the permanent darkness we almost got, is one of the most quietly terrifying things in all of science. Let us begin with the density of the early universe. In the immediate aftermath of the Big Bang, the density of matter and energy in the universe was extraordinarily high. As the universe expanded, that density dropped. The rate at which it dropped relative to the rate of expansion determined whether the universe would eventually recollapse under its own gravity, expand forever at a coasting rate, or expand at precisely the critical rate that balanced the two. Physicists express this balance with a parameter called omega, the ratio of the actual density of the universe to the critical density required for flat geometry. If omega had been significantly greater than 1 in the early universe, gravity would have dominated, and the universe would have recollapsed long before any stars could form, in a big crunch that ended everything in heat and density rather than cold and darkness. If omega had been significantly less than 1, the universe would have expanded so rapidly that matter never had time to clump into anything, producing the permanent structureless darkness I described. The actual value of omega in the early universe had to be extraordinarily close to 1 for a star-forming universe to result. Measurements suggest it was equal to 1 to within roughly 1 part in 10 to the power of 60 in the first second after the Big Bang. A deviation at the 60th decimal place would have produced a universe without stars. The precision required is almost impossible to convey. Then there is the strength of gravity itself. Gravity is the weakest of the 4 fundamental forces by an enormous margin, as we discussed earlier, but that weakness is not incidental. It is essential. If gravity were significantly stronger relative to the other forces, stars would form more easily, but would burn through their fuel almost instantaneously, living for years or decades rather than billions of years. A universe with stronger gravity might have plenty of stars, but they would all be so short-lived that there would be no time for planets to form around them, no time for chemistry to develop, no time for anything like life to emerge. Conversely, if gravity were significantly weaker, gas clouds would never reach the density needed to trigger nuclear ignition, and no stars would form at all. The strength of gravity, sitting in its precise position relative to the electromagnetic force and the nuclear forces, is one of the key parameters that makes a universe of long-lived stable stars possible. Move it in either direction by more than a modest factor, and the stars either never light or burn out almost instantly. The ratio of matter to antimatter in the early universe is another parameter that had to fall within a specific range. In the very early universe, matter and antimatter were produced in nearly equal quantities. When matter and antimatter meet, they annihilate each other, producing pure energy. If the early universe had produced exactly equal amounts of matter and antimatter, every particle of matter would have found an antimatter partner and annihilated it, leaving a universe of pure radiation with no matter at all. No atoms, no gas, no stars, no anything. What saved the universe from this fate was a tiny asymmetry, roughly 1 extra matter particle for every billion matter-antimatter pairs. When all the annihilation was done, that tiny surplus of matter was all that remained to form everything in the observable cosmos. Every galaxy, every star, every planet, every atom in your body is the residue of that 1 in a billion asymmetry. If the asymmetry had been slightly smaller, there would not have been enough matter left to form stars. If it had been much larger, the dynamics of the early universe would have been fundamentally different in ways that might have also precluded stellar formation. The universe walked yet another razor's edge. The initial density fluctuations, those tiny 1 in 100,000 variations in the primordial gas that seeded all subsequent structure, also had to fall within a narrow range. If they had been significantly smaller, gravity would never have been able to amplify them into dense enough regions for stars to form, even given billions of years to work with. The universe would have remained smooth and featureless forever, a perfectly uniform gas expanding into eternity. If the fluctuations had been significantly larger, the universe would have collapsed into enormous black holes almost immediately, before stars could form in any ordinary sense. The actual amplitude of the fluctuations, as measured with extraordinary precision in the cosmic microwave background, sits in the range that allows gravity to build structure slowly and steadily over hundreds of millions of years, producing stars and then galaxies, and then the cosmic web we observe today. It could have been otherwise. The physics does not require those particular values. They are what they are, and what they are happens to be compatible with the universe that lights up. Physicists sometimes call this the fine-tuning problem, and it is one of the deepest and most contested issues in all of fundamental science. The parameters of physics, the constants of nature, the initial conditions of the universe seem to be adjusted with extraordinary precision to produce a cosmos capable of forming stars and supporting complexity. Some scientists find this deeply suggestive, arguing that such precise tuning implies either a multiverse in which all possible parameter values are realized somewhere, and we inevitably find ourselves in one compatible with our existence, or something more intentional in the structure of reality. Others argue that our sense of fine-tuning is an illusion, that we do not yet understand the deeper physics that fixes the constants to their values, and that a more complete theory will show they could not have been otherwise. The debate is genuine, unresolved and important. But the raw fact underneath the debate is not contested. The numbers had to be close to what they are for the universe to have stars at all. I want to leave you with a feeling for what this means on a personal level as you lie here in the quiet of the night. The universe that exists, the one with stars and planets and carbon chemistry, and the long, improbable chain that led to you, was not guaranteed. It was not the only possible outcome of a Big Bang. It was one outcome, among perhaps many, that required an extraordinary alignment of conditions across multiple independent parameters simultaneously. The cosmic dark age ended and gave way to the first stars not because it had to, but because every number in the cosmic ledger happened to fall on the right side of a razor-thin line. You're here not just because of evolution, not just because of stellar nucleosynthesis, not just because of the formation of the Earth, but because the universe itself was configured, from its very first moments, in precisely the way needed to eventually produce something as improbable and as extraordinary as a conscious mind lying quietly in the dark, wondering how any of it came to be. We have arrived at the end of the journey, and I want to begin this final chapter by going back to where we started, all the way back to the darkness, because it looks different now than it did when we first entered it. At the beginning of tonight, the cosmic dark age was a story about absence, about nothing, about a universe that had not yet become anything recognizable. 200 million years of cold, featureless gas drifting in a darkness so complete that no analogy from ordinary life quite captures it. That was where we began. But now, having travelled through everything that followed, having traced the physics of the first stars and the forging of the elements, and the chain of origin that leads directly to you, I want to offer you a different way of seeing that darkness, not as an absence, not as a void waiting to be filled, but as a fullness so complete, so total, so perfectly loaded with potential, that it was, in the most meaningful sense, already everything. Think about what was present in that pre-stellar darkness. The hydrogen atoms drifting through it, atoms whose nuclei had been forged in the first 3 minutes of the universe, carried within them the potential for every chemical bond that would ever form in the history of the cosmos. The density variations folded into that gas, those 1 in 100,000 fluctuations seeded by quantum events in the earliest instance of the Big Bang, already contained the blueprint of every galaxy, every star, every solar system that would ever exist. The dark matter flowing invisibly through the primordial gas had already begun building the gravitational scaffolding that would organize those galaxies into the cosmic web we map today. The fundamental constants of physics, already fixed to their precise values in the first fractions of a second, already guaranteed that when the first collapse finally happened, nuclear fusion would ignite and stars would burn for billions of years rather than seconds. The darkness was not empty. It was pregnant with absolutely everything that was ever going to exist. There is a concept in philosophy and in contemplative traditions across many cultures that finds something sacred in the moment before manifestation, the pause before the note is played, the stillness before the wave rises, the silence that contains all possible sound precisely because no sound has yet been chosen. The cosmic dark age is the universe's version of that moment, stretched across 200 million years and the full extent of observable space. It was the universe in its state of pure potential, before any of that potential had resolved itself into the fire and light and chemistry and complexity that followed. And just as the pause before music contains in some sense all the music that will ever be played, the cosmic dark age contained, in a physical and mathematical sense that is not metaphor but literal fact, all the stars and galaxies and planets and living things that would ever come to exist. They were there, in seed form, in blueprint form, written into the physics of that cold dark gas, waiting. I think about this sometimes when I cannot sleep, when the house is quiet and the night presses close and the mind drifts toward the large questions that daylight keeps at bay. There is something deeply comforting in the idea that the darkness before the first star was not a problem to be solved, but a condition to be trusted. The universe did not panic in the cosmic dark age. It did not rush. It followed its own physics with perfect patience for 200 million years until gravity had done what gravity needed to do, until the gas had cooled to the right temperature, until the density had crossed the right threshold, and then, without drama, without announcement, in some unremarkable pocket of the primordial dark, a cloud of hydrogen began to collapse toward its center, and the first star was born. The darkness trusted its own process, and the process delivered. There is a parallel there to the experience of sleep that I find worth sitting with for a moment. When you close your eyes tonight, when the awareness dims and the thoughts begin to lose their edges, and the great busy machinery of the conscious mind begins to wind down, you are entering your own version of the dark. A stillness, a not yet, a state that feels from the inside like nothing, but from which something always emerges. You do not control what that something will be. You do not manage the process of rest or direct the work that sleep does in the body and the brain. You simply enter the dark and trust it. And every morning something has been restored that was depleted. Something has been processed that was unresolved. Something new, some arrangement of thoughts or feelings or memories, has quietly assembled itself in the stillness. The darkness does its work. It always has. Even the universe knew this, 200 million years before the first light. We are the universe noticing itself. That idea has been circling through this journey all night, and I want to hold it directly now, in the final minutes of our time together. The hydrogen that drifted through the cosmic dark age had no awareness of what it would become. The first stars that ignited had no knowledge of the elements they were forging. The supernovae that scattered those elements into the interstellar medium had no intention of seeding the chemistry of life. The gas clouds that formed our solar system did not know they were building a planet that would eventually host consciousness, and yet, here you are, a collection of atoms forged in stellar cores and scattered by cosmic violence, arranged by blind chemistry and billions of years of biological evolution into something capable of learning the history of its own origin. The universe looked at itself through you tonight. It heard its own story told back to it. In the quiet of the dark, by the very matter it spent 13.8 billion years assembling into a mind. That is not a small thing. That is perhaps the most extraordinary thing in the observable cosmos. I want to leave you with one final image as you drift towards sleep. Picture the darkness before the first star one more time. Not with dread, not with the vertigo of scale, but with the quiet recognition of what it was. A universe at rest before its great work began. Cold gas, drifting, patient, carrying everything it would ever need. The future written invisibly into the present in a language of gravity and quantum physics that would take billions of years to fully speak. And somewhere in that darkness already, in the only sense that truly matters, you were there. Not yet assembled, not yet conscious, but present in the hydrogen that would become the water in your cells, in the quantum fluctuations that would become the galaxy, that would become the solar system, that would become the Earth, that would become the conditions for your existence. You were there in the dark, waiting, 200 million years before the first star lit the way. Thank you for joining me tonight on this journey to the very edge of what we know. Thank you for staying with the darkness long enough to see what it contained. If this exploration moved something in you, if it left you feeling a little more connected to the vast and ancient cosmos outside your window, please take a moment to like the video or subscribe to the channel. It is a small gesture, but it helps more curious minds find their way here into the quiet and the wonder and the dark. The next time you look up at the night sky, remember that the stars you see are not the beginning of the story. They are somewhere in the middle of it. The beginning was darker and quieter, and in its own way more beautiful than any light. Sleep well tonight. You are made of everything the universe ever was, and it has been here all along waiting to tell you so. Good night.